Hi guys, I'd like to welcome all of us on board. So today we are going to look at this particular case of a wave-particle duality. And this, in a sense, stems from the de Broglie's hypothesis on the concept of a wave and particle, whereby de Broglie argued that electrons can behave as particles and waves at the same time. Now we are going to approach this particular discussion whereby we are going to use the concept of light, whereby we had seen that light, in a sense, undergoes some of the, or rather some of the properties of light is that it can be able to be interfered with. So it undergoes interference, diffraction, which basically gives it a characteristic of a wave. So we had looked earlier on on the concept of electromagnetic spectrum and given some of its characteristics in one of our videos. I'm going to put a link of that video in the description box so that we can be able to just do a complementary part of our discussion using that. So therefore, this particular aspect of light can be described using Maxwell's equations. We're not going to, of course, go into our deeper details of what this basically entails, but we're going to give just a few maybe similar examples or rather similar evidence trying to back up the concept of light, either having some characteristic of some of the aspects that we're going to discuss. So, but then we're going to see that we can be able to describe a light as a wave. There are some instances whereby this aspect of light or other electromagnetic waves or the behavior of electromagnetic waves are put into question, especially on some of the aspects like the black body radiation curves, which are going to give a particular behavior. And then we're going to see also that from the concept of a photoelectric effect that was explained by Albert Einstein, we're going to see the behavior of this particular light behaving as a particle. And therefore there was various explanation like for the last case that I've mentioned, whereby Einstein, of course, forwarded this idea of what we call a band of quantized radiant energy that he referred to as a photon, as it was being described by Max Planck, as we had mentioned earlier in one of our videos. And this, in a basis, assisted in describing, of course, what we refer to as the particle-like nature or the particle nature of light, whereby in a photoelectric effect we are going to see that this light is some aspects of momentum, which in classical physics basically describes the characteristic of what we refer to as particles. So therefore, in trying to describe this concept of a photon, we can be able to have a few, of course, equations or formula that we had used to describe this particular aspect in our earlier video. And we had said that from the Max Planck's argument, we said that this energy of this photon can be described using this specific formula. And we had expanded earlier and said that the implication of this is that this is a wavelength can be given as C over, sorry for that. This is a frequency, which is, this basically is a Greek word for mu, which implies frequency. This is a frequency of this particular particle or photon that is behaving as a wave. So therefore, this frequency can be given as C over lambda. So therefore, we can be able to expand this particular equation and give it as a product of H with a ratio of C over lambda. And therefore, from this particular illustration, we can be able to give this one a relationship. This is an Einstein-Planck energy mass relationship, whereby we say that Einstein described the mass of this particular particle as mc squared. So if we try to just expand this, we can just have this one from our mathematical illustration as mc c. But from classical physics, if you try to describe this particle as this particular photon as a particle, then we're going to have the product of its mass and velocity whereby we're going to assume that the velocity is the speed, its speed, then therefore we're going to represent this one as momentum. Therefore, in trying to describe this formula, then therefore we can be able to write E as a product of momentum and C. So therefore, we are going to have momentum being illustrated as the ratio between the energy and speed of light are given as such. And from this specific illustration, we are going to see that we can do a rearrangement of this particular formula and have this formula given as this is from this. I want to borrow from this particular equation and this last one, or rather this one that we have described. So the relationship between this one and this one, we can be able to give this particular case for E over C from here, which is equivalent to H over lambda. But we have said that E over C is equivalent to momentum. So therefore, we can describe momentum as H over lambda, which basically gives the relationship of the de Broglie's relationship over that particular particle for momentum, or rather the wavelength. Still, we can do a rearrangement for this as H over P. So from this particular description, the de Broglie made a speculation of a hypothesis of a particle wave properties of an electron, and therefore we are going to also see this one being developed into an idea whereby we're going to describe other particles, of course, which are going to have a wave-like nature for this particular case, similar to this electron that is being discussed. So we're going to see that this particular particle, which are moving at a very high speed, we're going to refer to them as relativistic particles, whereas the ones which we can be able to, of course, or the contrary to that is going to be non-relativistic particles. Now in this case, for the wave particle duality, we're going to consider two scenarios. That is for non-relativistic particles. Of course, this is going to be more elaborate on the theory of relativity. Non-relativistic particles, of course, from classical mechanics, we can be able to give the formula for momentum as the product of mass and velocity, basically, which is going to be mv. So therefore, if we try to consider this particular particle for non-relativistic particles as a wave, then therefore we're going to give it lambda, which is the de Broglie's wavelength, as h over the product of mv, which represents that particular momentum. But in this case, we're going to see that there's a different version that we can be able to give for these non-relativistic particles, whereby if you describe its motion or kinetic energy in terms of mv squared over 2, the relationship between this specific energy can as well be illustrated using Einstein's energy mass relationship, whereby E is equivalent to mc squared. So therefore, if we are able to expand this, we can be able to just have an equation that is mc squared equated to mv squared over 2, whereby if you try to manipulate this equation, we are going to have m squared c squared. So this is in multiplication over m on both sides of the equation. So therefore, I'm not going to affect this particular equation. So if suppose I say this is equation 1 and 2, and try to depict them as such, the second equation is a multiplication of m mass of this particular particle on both sides. So therefore, the value is going to be the same. But this equation can be written in terms of what we call P. So this is going to be given as so this is a cross multiplication to m c squared is equivalent to m squared v squared, and this is a square of momentum. So therefore, we're going to have p squared from this right side of the equation is equivalent to 2m, and this basically we are trying to equate E to the kinetic energy. So therefore we can just do a rearrangement. So having a root of, in order for us to find making the P the subject of the formula from this particular case, so it's a development from this side, making B the subject of the formula, we're going to have B being given as a root of 2m ek. So therefore from the de Broglie rearrangement of this specific equation, we can have B represented as 2m ek, that is the root of 2m ek. So therefore we can be able to represent the de Broglie wavelength as h all over 2m ke, which is kinetic energy. So that's just for non-relativistic particles, we can be able to represent its wavelength using that specific formula. So lastly, we're going to look at, for a contrast to this, which is a relativistic particle being described using that de Broglie relationship, and what kind of a formula can we be able to use for the wavelength, just as we have discussed for non-relativistic particles. So of course we're going to have these relativistic particles. So for higher energy particles, so in this case for relativistic particles, we're going to have the energy being given as, this is the square. Of course this is from of course the theory of relativity. We're going to have this one elaborate, as I've said, but for this one we're just going to use a formula and different variations of that specific formula in order to obtain what we are specifically looking for, which is lambda for higher energy particles. So the kinetic energy for this relativistic particle is going to be described using this particular formula. This is for energy minus or this is rest mass of that particular particle. And then we're going to see that from this particular case, we can be able to describe momentum using this formula for, or we can be able to derive a momentum from this formula, whereby this is going to be a result of Ek into Ek. I'm going to elaborate on this, so no worry about the different numbers. I'm just trying to wait on this. So this is a description of the PC that we're going to see this. So a variation of this specific formula is going to give us a way of representing lambda for relativistic particles. So therefore we can just try to pick this relationship from this specific point and try to see how we can be able to create a relationship for that. So if I try to find a PC from this specific point, then therefore I'm going to have a PC squared. I'm after momentum, so I'm after finding the relationship from the de Broglie relationship for wavelength from this particular momentum. So therefore I'm going to have a P squared C squared is equals A squared and then minus MOC squared from this specific part. I've just taken this to the other side of the equation. So therefore we're going to have A being represented as from the second, so this is the first one. From the second formula we can have E being represented as Ek plus M rest mass times that one. So if we try to make E squared the subject of this specific formula from this specific point, then we're going to see that we can do a substitution for just a minute. We can be able to do a substitution for this E squared in this specific sense. So from basic algebra we can just obtain the value for this for just squaring this specific equation. So we have E squared represented as Ek plus MOC squared. So the square of this from basic algebra is going to give us Ak squared plus 2 moc squared plus, and then this is going to be mo squared c to power 4. So that one, if we try to do a rearrangement for that and substitute it in this specific equation for p, we are given p squared as this one. So if you try to have this e squared being substituted for this is e squared, then we're going to have this particular equation transformed to p squared. C squared is equivalent to e gate squared plus 2m c squared plus m 2c4, and then we have this. We have just done a substitution for e squared for this, and then we have this section of our equation minus moc squared. So this is going to give us an overall equation for pc as the root, since these are squared, pc as the root over ek into ek, and then plus 2moc squared. Of course, this part of the equation that we had said is going to be substituted for, because there's a difference that we were supposed to, at this specific point, I guess this is m squared 4, yeah. Just so making PC the subject, then we're going to have e squared minus this one. So this was a rectification here for 2m squared, this one. So finally we're going to have this one c4. So therefore a minus of this and this will cancel this one out and leave this section of the equation, which basically is going to give us that particular case, the last one. So from this one we can be able to derive the relationship for a lambda, since we had said that lambda can be given as h over p, and therefore having us here that particular case, we're going to do a rearrangement for this formula and find that for relativistic particles we can be able to represent lambda as h over c. So this c is going to substitute for this pc, which is equivalent to the root of ek into ek plus 2moc, like that. So basically for higher energy or relativistic particles, we're going to use this lambda in trying to describe the formula for finding its wavelength. So this is going to be more elaborate when we're going to discuss on the theory of relativity that was advanced by Albert Einstein, but in a summary form, this is how we're going to tackle that one insofar as this particular case for the wave-particle duality is concerned. So catch us in our next video as we're going to look deeply into other areas concerning the aspect of the theory of relativity, which is going, of course, to compound our understanding on this treatment for particles that are for higher energy and, of course, non-relativistic particles insofar as this wave-particle duality concept is concerned. So that is it for today, guys. Bye. God bless you.